Okay, good morning, everyone. Just great to see you, all of you, again in a new MIST seminar. And today we have the pleasure to have with us Alan Wood from the University of Birmingham, who is going to talk about the ionospheric structures and drivers observed with the LOFAR Telescope and the ESA Swarm mission. And we are really excited because we have been trying to invite Alan for a long time, so we are really pleased that you are with us today. And also because he is going to be our host for the next spring meeting. I don't remember if it's in April or May, but I'm sure Alan will tell you later. So we are really pleased of having you today. And of course, just a reminder, be sure that you have your microphone disconnected and everything. And after Alan's talk, so we will have several minutes of questions and discussions all together. So yeah, welcome, Alan, and when you want, you can start.
Fantastic. Thank you very, very much. And thank you for inviting me along. And thank you to everyone for popping along to this seminar this morning. So this is going to be a seminar in two parts. Collectively, what we're talking about is ionospheric structures and their drivers. And we're going to start off thinking about some of those observed with the International LOFAR Telescope and then move on to talking about some of those observed by the ESA Swarm mission a little bit later. So starting off with LOFAR, I've got my co-authors up there to whom I am very, very grateful indeed. So let's just start off thinking about radio astronomy in general, first of all. So here is perhaps the most famous radio telescope in Britain, Jodrell Bank. It's a landmark up there on the Cheshire Plain. And one of the reasons it's a landmark is because it's so huge. And of course, that gives it benefits. It's got a large collecting area, so it gets a high signal intensity, and the large diameter means it gets a high angular resolution. So, of course, some decades back, people thought, well, let's see if we can make bigger radio telescopes. Let's see if we can get more detail still. And one nice little idea was, well, what would happen if we were to cover Central and Western Europe in a radio telescope? And of course, at that stage, the angular resolution would be absolutely fantastic. There'd probably be quite a lot of people who are quite cross because they couldn't see the sun because there's a big radio telescope above their heads everywhere. So perhaps it wasn't quite the best thing to do. But what LOFAR does is it has receiving stations across Central and Western Europe. And by putting together the information from these various receiving stations, then what we get is we get a radio telescope which has the angular resolution given by some of these very, very large baselines and the light gathering power given by the sum of the individual sizes of the arrays. So we've got the International LOFAR Telescope. What does it look like? Yeah, it looks a little bit like this, or a number of the receiving sites do anyway. And so there you can see one of the stations just down there. From a radio astronomy point of view, the science case behind it is absolutely fascinating. If you ever get a chance of a little read through it, I would highly recommend it. It includes all sorts of things to do with astrophysical transients, to do with surveying bits of the night sky, which have never been seen before in this level of detail at these wavelengths. And also this one here I find very, very interesting. Looking at the 21 centimeter hydrogen line, because that contains loads and loads and loads of useful information for radio astronomers. But in the most distant galaxies, it's so highly redshifted that we start seeing it in the radio part of the spectrum. So that was a science case behind it. And one of the reasons for building LOFAR down at mid-latitudes was it was thought that, well, the ionosphere is not quite a solved problem at mid-latitudes, but not terribly far off. And in fact, in the original plans that sat in behind LOFAR, there was one 3-month postdoc to be appointed to run a work package which would remove all the ionospheric effects from LOFAR using one postdoc across 3 months. Now, given the title of the talk today, you would be unsurprised to hear it didn't quite work out like that. And if we look at a little movie that looks a bit like this one here, you can see we've got 2 panels and we've got various natural radio sources, so things like distant galaxies, shown here as a function of right ascension and declination. And on the left-hand side, you can see what happens when the ionosphere is not disturbed. And on the right-hand side, you can see what happens under disturbed conditions. You can see these rippling effects. You can see some of these features starting to change in intensity and to appear to change in position. And sometimes this movie works very nicely, sometimes it doesn't. It probably depends a little bit on your device. So I've also got a still frame from a movie here, and I've put a yellow circle around just one of those radio sources, so you get an idea of the sort of variations that we get, that because of refraction within the ionosphere, it'll appear to move within that circle. So we have got a project called A World of Complexity, which is to investigate these ionospheric structures. It's funded by the Leverhulme Trust, to whom we are very grateful, and that supports myself, Richard Fallows, Gareth Dorian, and Ben Boyd. The Leverhulme Trust is ultimately backed by Unilever, and Unilever makes shower gel. So every time you go and buy some shower gel, you're helping finance this very exciting work. So today I'm going to focus on just one case study from the 14th of July 2018. And rather than looking at those sort of movies that we saw just now, instead I'm going to look at something called the dynamic spectra. And the dynamic spectra shows the signal intensity as a function of time and of frequency. Now, for undisturbed conditions, we would expect this to look fairly even all the way across this plot. We'd have a relative signal intensity of pretty close to 1.0. As you can see, though, there are some substantial variations. If we look at 1747 UT, you can see there's a large reduction in signal intensity here when we're observing Cygnus A. When we look towards the end of these time windows, that's not the case. And then we've got this rippling effect either side of this depletion. So we've got this observation here of Cygnus A from the 14th of July 2018. You can see there's a lot going on here, and that's what we want to investigate. Now, the station here is called RS508, and it's located in the Netherlands. And there's a whole bunch of LOFAR stations located across the Netherlands. So let's see what happens with those. We can see all the remote stations coded RS marked up here, and there's also lots of stations in the core, and we've just represented those here with one image because they're pretty close to one another. On this scale, they would appear to be co-located. I've put a red box around RS508. The color scale is slightly different to the previous plot, and that's to ensure that everything's comparable on here. And so the key point you can see here is you can see that this structure is different at the different stations. We can see that it varies. We can see that it's not the same everywhere across these various stations. I've just said that 3 times, haven't I? Still, it was an important point, so we might as well say it 3 times. If we look at some of the low resolution GNSS tech maps, and so you can see these here at 20-minute resolution, and if we zoom in across Northern Europe, then you can see there that we haven't got any indication of this kind of structure being present there at all. Now, of course, that's not surprising because these tech maps are fairly low resolution, and of course, much higher resolution products do indeed exist. However, I'm just showing this as an illustration to show it's a level of detail that we don't see in some of the commonly used products. Now, the observation we're using here is at low elevation, looking more or less northeast from the stations, and so we can look at a map like this, showing the rough positions of the stations we're thinking about there. And we're looking at low elevation towards the northeast. And that means we're not terribly far away from the Ionosonde and MF radar in northern Germany. So if we look and see what does the MF radar see at this time, so here we see power as a function of time and of range, then what you can see here is you can see we've got this nice strong enhancement in power up in the E region at the time of interest between 17 and 18 UT. If we look at the ionograms across that interval as well, they all look pretty much like this. And so what we can see here is there's that strong enhancement down at low altitudes that we interpret as sporadic E. And if we look at the virtual height, then that's around about 120 kilometers. If we look at all the ionograms across that hour, then we can plot the virtual height as a function of time, and we can see there's a little bit of variability there, but not a great deal. So to approximate it as being 120 kilometers is not bad. We can also look at FOES, and from that we can infer the density of the sporadic E layer. Now that does vary a little bit more across the hour, and so you can see the points plotted there on the bottom left, going up and down, a fair bit of variability. The red line is giving us the mean value, and the dashed blue lines give us the upper and lower limits. But nevertheless, we can say that the density of the sporadic E layer is around 3.3 times 10 to the 11 electrons per meter cubed. Okay, so for interpreting this as being due to a sporadic E layer, well, we'd also like to start with, we've also said that it's highly variable. And we want to see, is this structure moving around? So you'd look at a plot, so you'd look at an image like this and you think, well, maybe what we could do is we could cross-correlate. We could cross-correlate between the various stations, we could infer the speed, we could infer the direction, and we could find out how this structure's moving. You might think that, and if you try that, you'd find it's an absolute disaster. And the reason it's an absolute disaster is because of how quickly this structure is evolving. So what we're going to do instead here is we're going to take a very, very, very simple approach. Here I have just two stations, just as examples. RS508 on the top there, which is the one we've been thinking about quite extensively, and down at the bottom right is one called CS006, which is down in the core. And so all the core stations are pretty close to one another. So on the map at the bottom left, you can think of those as being pretty much co-located. Now you can see there's a large spike at the end of this feature. And we're just going to take that large spike and use that to try and infer a velocity. And just for fun, let's take another core station here as well. And if we do that, we find we get velocities of round about 26 meters per second, and we find that this feature's approximately moving northwards. But that's not the whole story, because the ionospheric pierce point is also moving, and it's moving because the radio source in the night sky, Cygnus A, is moving relative to the observer. And the velocity of the IPP is approximately 20 meters per second, approximately southwards. So you can see that when we look at these things collectively, it's not terribly far away from being stationary. So let's have a look and see if we can infer the extent of this feature. So what we're going to do here is we're going to just think about the core, and we're going to say, well, at around about 1727 UT, this depletion is pretty much as low as it goes in terms of signal intensity. So let's think about 1727 UT. Let's see where else shows has below the average signal intensity at that time. And where else has that average signal intensity below the median value at that time are shown within these red boxes here. And by looking at the position of the stations, we can say, for example, that it's seen by RS208 towards the bottom of the screen and not by RS310 right at the very, very bottom. So we will say that it finishes somewhere between those two stations. If we do that, we can say the north-south extent of this feature is 15 to 32 kilometers, somewhere in that range. We can't really say what the east-west extent is, only that it's greater than 7 kilometers because this feature goes out of the field of view in the eastward direction. Okay, so we can start saying how this feature, we can start attributing this feature to be sporadic E. We can then come up with an idea about its extent. We can say that it's probably not moving very much, and that we have these very different, and that we see it looking very differently at some of these stations. What we'd like to do to try and get a slightly better feel for what might be going on here is have a look at some modelling. Now, we're going to start off with some work done on a different study by my PhD student, Ben Boyd, which is currently in press at the Journal of Space Weather and Space Climate. So he was using observations of Cygnus A from the UK LOFAR station from the 15th of September 2018. And he's got a dynamic spectra that looks like this, with again time on the x-axis, signal intensity on the panel, and then frequency on the y-axis. Now, just the important point to note here is the frequency axis is now going the other way around, with the larger frequencies towards the bottom of the plot, as is commonly done within radio astronomy. So you can see some quite interesting features there, and he was investigating these. And to investigate what might be causing these, he decided to start off using this model from 40 years ago, where the ionosphere is treated as a thin phase screen, and we put a sine wave in there to represent a traveling ionospheric disturbance. And so you can see the electron density depletions and enhancements, and you can see the radio waves being focused to a point. So he started off with a simple model, because why not start off with something simple and see how much we can explain with a simple approach? And he couldn't explain everything, but he could explain a lot. And so when we look at the observations and the model output, you can see some strong similarities there between the feature and the model. Other features couldn't be represented so well at all. So Ben extended this model. And one of the ways he extended it was, instead of just putting in a sine wave, said, what happens if we also add the first harmonic to that sine wave? And when he did that, he was able to represent some of the other features as well. Now, I'm not going to say any more about his work because I don't want to steal his thunder, but I do want to point you to his paper in the Journal of Space Weather and Space Climate, which is currently in press. Now, what we've done within this study from the 14th of July 2018 is to take that model and take the sine wave out of it and put in some other functions. And one of the functions we put in was a Gaussian density enhancement. And by putting in a Gaussian density enhancement, we wanted to see, could we represent this? So how do we define our Gaussian density enhancement? Well, we need an amplitude for it. And we chose 1 × 10⁻11 electrons per meter cubed, because that then roughly corresponded to the variations we were seeing with the ionosons. And then in terms of what that means in terms of a phase change, we've got that marked up as well. We started with the standard deviation for this Gaussian of 1 kilometer, because why not? You got to start somewhere. The altitude we're fairly happy with from the ionosons. The elevation of the source we know very, very well because we know where it is in the night sky. And the velocity of the plasma we have as well. And so what we can then do is we can then model that. And we get something that looks like this. So it's not the same. I'm not for a million, I'm absolutely not saying that the model is the same as the observations, but it's not completely different either. Now, the first big difference you can see is the model assumes that the path to the there's no asymmetry here in the model. Why is that? Well, the model assumes that the path to the source is perpendicular to the phase screen. What happens if that's not true? If that's not true, and then we add a density enhancement here, well, then we're going to get an enhancement of the signal intensity on the trailing edge of the feature, just from optics. So it's not surprising that given our assumption, given the assumption in the model that the source is directly overhead, perpendicular to our phase screen, it's not surprising we don't get the asymmetry. We can explain that nice and easily. How about the other bits and pieces in here? How reasonable are these ideas? Well, one way to think about that is some of these numbers are a bit vague. So what happens if we vary them? If we change the amplitude of the Gaussian, we still get the same patterns. We get some slightly different intensities, but we get the same patterns in here. If we change the altitude of the E layer and try putting it up in the F region, for example, again, we see the same kind of patterns, slightly different shape and structure to them, slightly different width to them, but we see some of the same patterns coming up here. If we change the velocity of the plasma, this changes the width of the feature when you look at the time scale, but the basic structure of it remains. Unfortunately, the thing this seems to be most sensitive to is the standard deviation of a Gaussian. And with that particular parameter, we picked a number that seemed like a good idea. And so you can see that that actually does have quite an effect in here. So it's not unreasonable to maybe model this as a Gaussian, but we can't absolutely guarantee that's exactly what it is. What we want to think about next is the origin of the structure. What might be causing it? And what stands out from the heliophysical conditions on this day is that conditions were quiet. So if we look here, we can see KP was 1, AA was 2 nanotesla, DST was -3 nanotesla. When we look at measurements of solar activity, there's no significant solar flares. The F10.7 centimeter solar radial flux was also quite quiet. And when we look at the solar wind conditions, the thing that most stands out about these was there's nothing huge that stood out about them. Nice slow solar winds. As I said earlier, we're attributing this to be sporadic E, and that could be caused by wind shear or possibly meteors, and work is underway to investigate that. And one of the other things we want to use in combination with that is look at some higher resolution tech maps in there as well. So as we come to the summary for the first part of the talk, we're saying that LOFAR can infer the presence of these small-scale ionospheric structures, works in progress to look at the drivers of these. Now, at this point, what I'd love to do is launch into a statistical study and say, okay, well, that's one example. What happens if we look across a year? When do these structures tend to occur? Do the climatologies of them match up with the climatologies of things like medium-scale traveling ionospheric disturbances, for example? And in a few months' time, hopefully I'll be able to do that, but not yet. That is our next step. So that means I'm going to actually stop this particular slideshow, and we're going to dive into the next of these two presentations. So this was a talk in 2 halves today, which is then where we do move on to a statistical study. And the statistical study in question is to do with the ESA Swarm mission. So I will just reshare my screen. Here we go. And so, yeah, and so we're going to move on to thinking about some results from the ESA Swarm mission. And the project here is called Swarm VIP, which stands for Variability of Ionospheric Plasma. Before I say anything more about this, I should say a huge thank you to my gigantic and ever-growing list of co-authors on here. The Swarm VIP project is led by the University of Oslo. It's funded by the ESA Swarm plus 4D ionosphere framework. And as you can see, there's a large number of partner institutions there. University of Oslo are the lead organisation. There's also INGV, the University of Birmingham, GMV Innovating Solutions, and Nottingham Trent University. So huge thank you to all of them. So the Swarm mission originally comprised 3 satellites in near polar orbit, observing the topside ionosphere. And they're able to observe the variability of ionospheric plasma. And there's some products that have been created that are very useful for looking into this. And what we're doing within this study is we're applying the technique of generalized linear modeling, a statistical modeling technique. And we're asking 2 key questions. Which combination of driving processes best represent the observed variability? And then can we create a model of the variability of the ionospheric plasma? Okay, so first of all, what is generalized linear modeling? Well, a linear model is a special case of a generalized linear model. So we can see a linear model of the form y equals mx plus c, where we've got our dependent variable on the left-hand side, the thing we want to predict. We've got our independent or explanatory variable on the right-hand side. That's what we want to predict it from. And there's a couple of constants in there as well. A multivariate linear model is also a special case of a generalized linear model, the same as the linear model, but now with multiple drivers there on the right-hand side. And our equation for a generalized linear model looks very similar. The differences are that the dependent variable does not have to follow a normal distribution, and therefore, and if that's the case, the equation on the right-hand side may well have a different form. Okay, so the first thing we need is a measure of the variability of the electron density. And we're taking this from a previous swarm project called EPIA, which created some of these measures. The first of those is called grad NE at 100 kilometers. And this is formally defined as the electron density gradient in a running window calculated via linear regression over 27 data points for the 2 Hertz electron density data. So that's quite a mouthful, but it basically boils down to a measure of the variability of the electron density on a horizontal spatial scale of 100 kilometers. Grad NE at 50 kilometers and grad NE at 20 kilometers are similar, but going down to the smaller spatial scales. We're also interested in modeling the electron density itself, and this thing here called the EPIA index, which is defined as the product of the rate of change of the density index in 10 seconds and the standard deviation of the electron density in a running window of 10 seconds, which is again quite a mouthful, but it basically boils down to a measure of the variability of the ionospheric plasma on a horizontal spatial scale of about 80 kilometers. And because we expect the driving processes to be different at different latitudinal regions, we're modeling the polar, auroral, mid-latitude, and equatorial regions separately. There is, however, a problem. And the problem is that if we just look at successive observations of, for example, gradini at 100 kilometers, then those are not going to be independent of one another. You can see we're applying linear regression across 27 data points. So it means there's going to be some particular interval over which these data are not going to be independent. But based on the ionospheric structures, the lack of independence stretches much further. So if, for example, we look at this plot using observations of gradini at 100 kilometers from Swarm A, this is in the mid-latitude region in July 2019. You can see there's some quite large structures there. For example, this one here. And this one is wider than the 27 data points that we used to create gradini at 100 kilometers. So we need to do something to ensure that our data points are going to be independent to feed into our generalized linear model. So what we did is we took 33 days of data and manually inspected those. Those days were chosen to cover a variety of local times, solar activities, and geomagnetic activities. And let's see what's the largest scale size that we see within these data. And these were the results. So for example, in the mid-latitude region, the largest scale size we saw extended over 300 seconds of time. And based on the motion of Swarm A, that corresponded to a spatial scale of 20 degrees latitude. Now, I want to make very clear that we do not necessarily believe that these structures are real. We do not think there's this big structure spanning 20 degrees latitude sitting there at in the mid-latitude region. But what we do think is if we only take 1 point in per 20 degrees latitude in any individual orbit, we can be confident that our data points are independent of one another. So that's what this is about. It's about being confident that our data points are independent of each other. So what we did is we took 2 years of data from Swarm A, covering a period from 2014 into 2015. If you're wondering why we started off at that rather strange looking date, we started off at that date because it was the first day that the Swarm EPA data product is publicly available through the ESA website. There are some data points from earlier in 2014 as well, but this is the first date that you can just go up and download this data yourself. So 16th of July 2014 to 15th of July 2015, and again, the whole of 2017. And those years were chosen to cover a period of higher solar activity and a period of lower solar activity. Now, in each calendar year, we sample all local time sectors and all seasons. So the dependent variables we wanted to model were gradini at 100 kilometers, gradini at 50 kilometers, gradini at 20 kilometers, the electron density, and the EPA index. Now you can see that we're now looking at the modulus of gradini at 100 kilometers, 50 kilometers, and 20 kilometers, and that's because it doesn't make sense to think about these structures being that the gradient to this was to remove the effect of the spacecraft flying through these structures in different directions. So we just looked at the absolute value. Now, the first thing we need to do is we need to see which distribution is appropriate for our data sets. So let's start off looking at gradini at 100 kilometers in the polar region and seeing what distribution we could choose. Now, to aid the choice of distribution, we use things called quantile plots or QQ plots. So the idea behind a quantile plot is you put the quantiles of your input sample on the y-axis, and on the x-axis, you put the quantiles of a distribution. And how you create this distribution is you assume that you know what your distribution is for your input sample. So in this example here, we're assuming it follows a normal or Gaussian distribution. And so if it does follow a normal or Gaussian distribution, then we can find a mean value, we can find a standard deviation. So based on that mean value and standard deviation, we can create some synthetic data, take the quantiles of that, pop that on the x-axis. If this all works nicely, then we get all our points lining up along the red dashed line, which is the x equals y line. And what you can see here is it does not work very nicely when we consider the normal distribution. So we tried various other distributions, and rather unfortunately, it didn't work nicely for any of them. So here, for example, is the gamma distribution. The gamma distribution is then defined by the shape and scale parameter. So we took our data, we assumed it was a gamma distribution, found the shape and scale parameter, then created synthetic data and put those quantiles on the x-axis. And you can see that these points depart significantly from the x equals y line. And what that means is when we look at those points within this red circle here, you can see the quantiles of the input sample are always greater than the quantiles of the gamma distribution. This tells us that our model is going to always underpredict those larger values. And so this is not a good choice. And unfortunately, none of those distributions are a good choice. So what we moved on to do is to look at to transform the data and look at some transformations. An example of a transformation is instead of modeling the absolute value of grad n e at 100 kilometers, we could take the natural log of it. And we tried various logarithms, exponentials, powers, and roots. And what we found is that the nth root of the gamma distribution was a good choice for everything we're trying to model in all the different latitudinal regions. When we're talking about grad n e and its various versions. So you can see here's our final choices. So it was always the gamma distribution and the nth root of that. When we came down to the electron density, then the normal distribution and the nth root of that. And for the EPA index, which is then takes discrete values, we use the Poisson distribution. So we've got our choice of data, we've got our choice of distribution. So now we need our explanatory variables. And so what these explanatory variables are, they are proxies for the processes that we think are driving the variability of ionospheric plasma. And so I'm not going to go through all these in detail because we would run out of time. But you can see here that we've got measures of the solar wind, of the interplanetary magnetic field, of the solar wind's coupling functions, of geomagnetic activity, of solar activity. And then we've also got the polar cap index in there, and we've got the solar zenith angle, magnetic local time, geographic latitudes, and magnetic latitudes as well. So what's our modeling method? Well, the question we're trying to answer with our multi-term model is which combination of heliogeophysical proxies and hence which processes best explain the variability of the ionospheric plasma that we observe. So what we do is we test the statistical significance of each of those proxies, how statistically significant the relationship is between those proxies and the dependent variable. And we find the one that has the most statistically significant relationship to the dependent variable. And we take that heliogeophysical proxy, which best explains the variability, and we pop it in the model. Then what we do is we say, okay, we've got a model which now has one term on the right-hand side. Let's take that, let's trial everything else we've got to make two terms. And as long as there isn't a strong correlation between those terms on the right-hand side, those two terms, we'll find the one that has the highest statistical significance and pop it into the model. The terms on the right-hand side need to be independent of one another. So that's why we look at the correlations as well. And what we do is we exclude anything from our analysis if it has a correlation of greater than a modulus of 0.25 with anything that's already in our model. That doesn't mean we think a correlation of 0.26 is real, but it means at 0.25 we think it's not something we need to be terribly worried about. And we continue this process until there's no more proxies that make a significant difference. There's nothing that is statistically significant at the 5% level when added into the model. So we go through this process. This process is then this process of adding in one term at a time, finding the most statistically significant term, popping it in the model, checking to see what else is not significantly correlated with it, testing all of those, finding the one which gives the most statistically significant relationship to the dependent variable, popping it in the model and continuing this process until there's nothing left. What do our models look like? Well, the terms in the models look rather like this. So it's a very, very big list. Let's just take one and look at it as an example. So here we go. Here's our model of grad n e at 100 kilometers. And you can see there, we've got our dependent variables on the right-hand side. We've got various measures of solar activity, solar zenith angle, this function for the day of year, geomagnetic activity, solar wind conditions, etc., etc., etc. And we create these models for these different dependent variables and different latitudinal regions. So you start thinking, well, it's quite a complex model. Is that level of complexity justified? And to test whether that's true or not, we went through the process of model optimization and evaluation, also known as validation and testing. So you can see what we've done here is we've picked various other days around the training data set. And what we're doing with those is we're then having a little look to see what happens if we try and optimize these models. So what's our optimization strategy? Well, the first stage of our optimization strategy is to refit the models. And then we can identify any terms which are no longer statistically significant at the 5% level and remove them. Because with any statistical model, there's always the chance of something sneaking in that shouldn't be there. If you work at the 5% significance level, that means you're 95% certain about any of your results. That means you're 5% certain your results are wrong. Therefore, we want to see, has anything snuck in here that shouldn't be there? So that's our first test. Our second test is then to look at the AIC. The AIC, which is an information criterion, is based on the trade-off between model performance and model complexity. So the question we're asking is, okay, all these terms might now be valid, but are they justified? Is this level of complexity sensible? And the AIC looks at the trade-off between model performance and model complexity. It's based on the log likelihood and the number of parameters. And how this is often used as a tool is to say, if we've got a series of nested models, which has the lowest AIC. What do we mean by nested models? We mean, suppose you've got a model with 7 terms in it. What happens if you remove term 7? What happens if you remove term 6? What happens if you remove term 5? Where do you get the lowest AIC? However, it's a tool, and we want to use it sensibly. And so there are decades and decades and decades of research that says things like the latitude is going to be important. Some measure of local time or solar zenith angle is likely to be important, as is solar activity, as is some measure of geomagnetic activity or the solar wind. So if based on the tests using the AIC, we were going to remove, for example, every measure of solar activity, we don't let it remove that measure of solar activity. We keep at least one of those in. So let's have a look at that as an example. So there's our example model we talked about just now. If we go through that process of refitting and removing any terms which are no longer significant, we actually lose 2 terms from this model. Then we go through those tests to say, is this level of complexity justified? And we lose another term from the model. So the next thing we need to do is we need to evaluate the model. And to evaluate the model, we're going to use various goodness of fit statistics. The first of those is a measure of accuracy. And for that, we're going to use the root mean square error on a relative scale. And by putting it on a relative scale, it means that if we've got a RMSE of 1, then it means the differences between the observations and predictions are the same size as the predictions. So we want it to be much smaller than 1. We're going to look at a measure, we're going to look at the bias. And for that, we're going to use the mean error. What we're going to do here is to ask, does the model consistently overpredict or does it consistently underpredict? We want this to be 0. Anything other than 0 means we've got problems with our model. We're also going to look at the precision. The precision is the ratio of the standard deviations. And so we want the standard deviations in the model and in the observations to be similar. If they're not similar, then we've got a bit of a problem here. If we end up with the ratio of the standard deviations in the model being too small, it means we're not modeling all of the variability. There's not enough spread there in our model values. So we want this to be as close to 1 as possible. And then we've got our measure of association. Are we capturing the trends? And to look into that, we're using the Pearson linear correlation coefficient. Okay, so what do our goodness of fit statistics look like? Well, they look a bit like this. So this is a huge table. I'm just going to pull out a few things from it. There's some good news. The good news is the root mean square relative error is substantially less than 1 in almost all cases. So our measure of accuracy is quite good here. The relative mean error shows no significant bias. Most of these values are fairly close to 0. Also good news, but this is where the good news ends. When we look at the precision, you can see these values are all much less than 1. That means there's not enough spread in our model values. We're not capturing all of the variability. And when we look at the correlations, well, some of those are quite good. Some of those are certainly not. And so we're not capturing all the trends. Why are we not capturing all the trends? We're attributing that to this issue with precision, that we're not capturing the spread of the observed values fully. It's not a surprise we don't. This is a statistical model. It can only capture the deterministic component. It can't capture the random component. But there's other possibilities as well, which are perhaps more worrying. The first of those is to remember that the explanatory variables are proxies for the processes, not the processes themselves. And therefore, some information has been lost as we've gone from a process to a proxy. And perhaps that's leading to some of the variability not being captured by the model. Then there's another question here. Is there a missing process? Now, in terms of the heliogeophysical parameters that I showed you that we were testing as explanatory variables, there were no thermospheric terms in there at all. So we did everything again, now including some observations from Swarm of the thermospheric density. And while we're doing that, we thought we might as well test the observations of some of the current systems from Swarm as well. The terms in the models now look like this. You can see in loads of these models, the thermospheric density came up as the first term in these models. It was the most statistically significant. You can see there's some places there where no new model was fitted. And the reason for that is the F10.7 centimeter solar flux was more statistically significant than the thermospheric density. And these two things were correlated with one another. So if we put the F10.7 centimeter solar flux in, we then didn't put the thermospheric density in. So for those places where no new model was fitted, the thermospheric density was still important, but it didn't make it into our models. Our models were the same as those we had before. When it comes to the current systems, you see those only cropped up twice and right down the end of the list. So we want to see, what did that do to model performance? So I've got these goodness fit statistics of the same form as before. They're perhaps not terribly easy to interpret like this. So instead, what I've done is I've looked at the difference between what we had before without the thermospheric density and the current systems and what we've got now. And here, positive values indicate larger values of the statistics in revised versions of the models. Now, when we're thinking about the root mean square error and the mean error on relative scales, the changes are very small. It makes next to no difference. When we're thinking about the precision, the changes are again fairly small. But we do have some slight increases here. So we are capturing more of the variability. And when we look at the correlations, these are again slightly higher. So capturing more of that variability seems to be good news for capturing the trends. Now, the thermospheric data product we used here is limited. It has a temporal resolution of 30 seconds, and Swarm A moves quite a long way in those 30 seconds. And so that 30 seconds corresponds to spatial resolution of about 2 degrees, or latitude, or about 220 kilometers. And of course, there's nothing in there about the temperatures of the winds. And we think if we tested if we tested some of those things, if we test a higher resolution thermospheric data product or the temperatures of the winds, then that may mean that this will better represent the variability of the ionospheric plasma. So to conclude, these statistical models allow reasonable predictions of the ionospheric plasma and the variability in this plasma to be made. The accuracy of these models is high and they don't show significant bias. Now, the models do not capture all of the variability of the ionosphere. They cannot capture the random variation. And there's at least one driver, the thermosphere, which was missing there. We've added that we've added some information about that thermospheric driver, but the thermospheric data product is somewhat limited, and a new data product might really help in here. Now, just before we conclude, I want to pop up an advert. Spring Mist is going to be held here at the University of Birmingham between the 3rd and the 5th of April 2023. We'd love to welcome you here to our lovely campus. We'll be hosting that at our Edgbaston Park Hotel, which is a lovely venue, and it's going to run from lunchtime on the 3rd to lunchtime on the 5th to make it nice and easy for travel. Full details will appear on the MIST email list later in the autumn. Abstract submission opens in January 2023. I could tell you lots more about our lovely conference facilities and our wonderful campus, but the only thing I want to mention is we have a dinosaur museum. You've got to love a university that's got its own dinosaur museum. So on that note, I think we will finish. Thank you very much for your attention, and I'd be delighted to take any questions.
Cool. Thank you very much, Alan. Definitely, I mean, I will go definitely only and exclusively for the museum and then miss meeting. Anyway, thank you very much for your talk. It has been really great. I think I learned a lot today as well. And actually, we have several questions on the chat for you. But let me open the chat a bit bigger because when you stop sharing the screen, my configuration changed. So 1 second.
I've just seen one pop up from Mario. Mario was saying, I wonder where the dinosaur reference is going to come in. Mario knows me very, very well.
I think that my priorities now is the dinosaur first and then Miss, but I agree. Okay, so there is a question from Matt Owens. So he said, great talk. Have you thought about trying some causal inference methods? Might help with some mutual drivers of ionospheric variability, like for example, the solar wind coupling likely correlates with F10.7 to some degree.
Yeah, that's a really good point, and it would be a really, really, really good next step. One of the things that we do want to try as well is that there's a higher resolution thermospheric density data product available in the Swarm, available from Swarm, and but in terms of how that data product is created, it also includes information on KP and the F10.7 centimeter solar flux. And so we've got the Swarm data quality workshop in, well, actually this time next week. And so we want to chat to some of the people behind that product and see if that would be useful as well. But yeah, I know I've diverted something from Matt's original question, but it's a really, really good suggestion. It would make an excellent next step.
Cool. So next question is by Edmund Henley. So it's about the Swarm VIP. So you remind invariance, can you say anything constrain the temporal scales this is on? Asking us, wondering whether there may be looking at STH faster than daily F10.7 driving direct change in ionization, like for example, X-ray flux.
Now, at the moment, we can't, but again, it would be a really, really good avenue to investigate, because when we're just using Swarm A, which is what's been used in the study that's shown here so far, it's difficult to separate the temporal and spatial effects, because we know that because, you know, for example, we'll look at a structure which might be seen as, say, Grad-N-E at 100 kilometers. We're looking at a spatial scale of 100 kilometers, but of course that corresponds to a temporal scale as well because of the motion of the spacecraft. But if we use Swarm A in combination with Swarm C, then because these spacecraft are so closely spaced, we can start trying to separate spatial and temporal effects, and that would be a very, very useful thing to have a look at next, I think, and to and to see what we could say in answer to Edmund's question.
Cool. Well, there is another question by Edmund as well. So now it's about LOFAR. So do you have any explanation for the shoulder to the left of the evacuated area? Was this explained by the non-orthogonal phase screen, or was that just enhancing intensity of the trailing edge, I assume different to the shoulder?
Ah, excellent question. Let me go back and I will bring up one of those plots. Let's see where it's lurking. Here we go. Let's go for maybe this one. And I will just reshare my screen. Where's it gone? So the question was about here we go. The question was about the trailing edge, which we can see over here around about 1750 UT. So what we were attributing this to is we were attributing it to the idea that if we've got the source at, say, low elevation, so what we've got the ray paths coming down through the ionosphere like this, then if we have a uniform ionosphere, no problem at all. But if we've got a structure in the ionosphere, maybe a density enhancement, then what we're going to get is we're going to get refraction within that density enhancement, and we're going to get enhancement in signal intensity, say on the trailing edge on the right hand side here, which if this feature is moving along to the left, say, will then be on the trailing edge of this particular feature. So we haven't gone beyond that. We've just made that argument based upon, based upon refraction of the radio waves. But we've made that argument to then say that may be why we've got this asymmetry here in the dynamic spectra, because we've got a rippling effect on both sides. If I were to zoom in on the bit on the right hand side, you can see a rippling effect that looks very much like the rippling effect on the left hand side, but just on a compressed spatial scale, compressed temporal scale. And this was quite a high resolution observation in terms of the time resolution. It's about 96 milliseconds, and so we can still see that rippling. And so we're attributing the asymmetry to those, to the refractive effects. I'm not sure that's quite answered Edmund's question actually, but we haven't gone beyond that. Yeah.
Okay, maybe Edmund can open the microphone if he wants to comment something else. I don't know.
No, that sounds fine to me. I wasn't thinking. Thanks, Alan.
Oh, thanks, Edmund.
Okay, so there is another question. Oh, there is the dinosaur by Mario. But yeah, there is another question by Elko Dornbos. Hopefully I pronounced the name properly. So he said, great talks. And regarding your comment toward the end, the swarm DNS POD thermosphere densities have a much worse resolution than the 30 seconds cadence of the dataset suggests. So there are more details in a paper that is on the chat. And then he said, using the old DNS ACC or new Grace thermosphere products that overlap with swarm might help. And oh, sorry. Sorry, my chat changed to other place. And then the second one is, and a question bringing your two talks together, is there any interest in studying swarm LOFAR conjunctions? Will it make sense to study the data that way? There's two questions in one.
Yep, absolutely. First of all, thank you very, very much for that paper. We'll have a good look at that and build that into our work and discussion. So yeah, thank you very, very much. I think it's because of what we've done to ensure the independence of our data points in the original data set that we're modeling from, it means that we're not actually taking the thermospheric densities every 30 seconds. We're taking the points that then match up to our lower resolution database. So it's not going to give us a problem there in terms of in terms of lack of independence of the data points in our explanatory variables. But you're right, that's a very useful paper, and that's something that we'll have a good look into. So thank you very, very much for sharing that. In terms of looking at conjunctions between Swarm and LOFAR, absolutely. We've started doing some work on that, and we haven't got any results on that yet, because one of the problems is some of the things we see with LOFAR rock up relatively rarely. So we're still working our way through everything and looking for that magic day when we see something in LOFAR and we've got our conjunction with Swarm. The data sets are so extensive, but it must be in there somewhere. It's just actually working through it to try and find where those live that take the time. But yeah, that will be a good, exciting thing that we want to do.
Good. So I don't see any other questions. Let me see if anyone else has raised the hand. I don't see any rise, so yeah, last chance for questions for Alan. Otherwise, I will say, yeah, we can maybe finish here. So I think it has been really a great talk, and we are very pleased to have invited you, and you give a very excellent two talks. And I mean, I will hopefully in the next hour, I will upload this seminar to YouTube. So I'm pretty sure there will be more people later visiting and maybe asking more questions after that directly to you. So thank you so much again, and see you, all of you, next month on the first Tuesday at 11. Good.
And thank you all for coming along, and thank you very, very much for inviting me. Thank you.
I'm looking forward to see you on the dinosaurs in Birmingham in April.
Excellent. I look forward to seeing you then.
Cool.
Thank you.
Thank
Bye.
you all.
Thank you. Bye-bye.
Bye.
Thanks, Helen.